Hello! Every one of us encountered the geometric sequence and series in school or university. We've seen how useful it is and used it in various applications. Today, we will check some applications for it and see how powerful the series is. As a quick reminder, the geometric sequence is a sequence that has a constant common ratio between each term. If we divide the next term by the previous term, we will get that ratio. The geometric series is simply adding up these terms. Let's start with its application in probability. The geometric random variable is the number of tries until we encounter a success, and each random variable has a probability mass function assigned to it. We call it the PMF. For the geometric random variable, its PMF is the following. Since it's the amount of tries until we reach a success, we multiply the probability of failures and lastly the probability of success. If the failure and success events are independent of previous tries, then it's simply multiplying the same probability of failure k minus 1 times and 1 for the success. If we graph the PMF with respect to the tries until a success, call it k, we notice a decrease in the probability as we move along the graph. This makes sense because as the number of tries until a success increase, the probability of it happening decrease. Another way to think of the decrease is to keep in mind the amount of possible probability sequences as the amount of k increases. At the beginning, it's only 2 sequences, either a success or a failure. When k is equal to 2, it's 4 sequences and we are interested in only one of the sequences. Failure, then a success. Go to k equal 3 and now it's 8 sequences and we are interested in only one of them. We see that as we go further, the number of possible probability sequences increase by 2 to the power k, with the common ratio being 2, and the probability of only one of them happening become less and less. In the next application, we need a famous result, the sum of the geometric series formula. If you are familiar with the telescoping sum, the following method uses it to find the formula. We start with the sum and multiply both sides by 1 minus r. We expand the right side and the terms will cancel out similar to a telescoping sum, leaving us with the formula for the sum of the geometric series. This result will be useful not only in this application as we will see later on. Jumping to computer science, the need to represent integers in binary is obviously needed for computers, and the method to do that uses a series of power of 2. It's a geometric series that we get to choose which term to include. The terms we picked is simply represented by 1 in binary. There exists a theorem that proves the existence and uniqueness of the representation of integers as a series of power of 2. The theorem statement is the following. Given any positive integer n has a unique representation in the following form, where r is a non-negative integer. The coefficient cr is equal to 1, the rest of the coefficients could equal 1 or 0. What we need to do now is to prove the theorem. To do that, we need to separate the proof into 2 parts, the existence part and the uniqueness part. We start with the existence part. In this part, we need to use strong induction to prove it. To prove a statement by strong induction, we need a couple of steps. The first is to prove the base case is true, then assume it's true for all cases from 1 to k, and finally prove that we can get the k plus 1 term. The base case is the smallest positive integer, which is equal to 1. We let r equal to 0 and set the coefficients starting from r minus 1 to 0. We end up with a representation that's equal to 1. On to the next step. If pk is true from 1 to k, then prove pk plus 1 is true. Integers could either be even or odd, and so we need to split this part into 2 cases. The first case is k plus 1 is even. We start with the integer k plus 1 divided by 2. This integer could be represented by assumption, since it's less than k and bigger or equal to 1. We represent it and multiply both sides by 2, and we get the representation as a sum of power of 2, if k plus 1 is even. The second case is when k plus 1 is odd. We choose k divided by 2. It can be represented by assumption, since it's less than k and bigger or equal to 1. We represent it and multiply both sides by 2 and add 1. We end up with the representation as a sum of powers of 2 in case of k plus 1 being odd. So regardless of k plus 1 being even or odd, it could be presented as a sum of powers of 2. Now we need to prove the last part, the uniqueness part. To prove that, we suppose there's an integer n with two different representations. If we equate both representations and reach a contradiction, then the uniqueness statement is true. We equate the two representations. R and S are non-negative integers. CR and DS is equal to 1 and the rest of the coefficients could be 0 or 1. If both representations is not bigger or smaller than each other, then they are equal. The first part is to assume that S is bigger than R. The second part is to assume R is bigger than S. But since both parts can be proved exactly the same, the proof includes the first part, S bigger than R. You see this in math proofs when the second part of the proof is the same as the first part of the proof. They prove the first part only and add the sentence without loss of generality. So assuming S is bigger than R and both S and R are non-negative integers, this implies that S is bigger or equal to R plus 1. Since S is bigger than R, it is bigger or equal to the next integer. The biggest that the representation could be is when all coefficients is equal to 1. We use the following inequality to represent this fact. When all coefficients is equal to 1, we use the formula for the geometric sum and end up with the following result. This result is smaller than 2 to the power s, using the fact that r plus 1 is smaller or equal to s, and using these integers as an exponential of base 2 does not change the inequality, since the exponential function is strictly increasing. If s is bigger than r, the first term of the representation using s alone is bigger than the entire representation using r. Therefore, if the entire representation using r is less than 2 to the power s alone, it is for sure smaller than the entire representation using s. This contradicts our assumption that both are equal, and therefore the theorem statements about uniqueness is true. Moving on to calculus, a lot of proofs uses the geometric series to confirm theorems. Since we are talking about calculus, we need to take the result about the sum of the geometric and take its limit. We see that if the ratio is less than 1, the formula's limit exists. Now we know that the limit exists, we move on to the ratio test. The ratio test states that if the limit of the ratio of the next term and the previous term is less than 1 and bigger or equal to 0, then the series converges absolutely. Let's check the proof of the ratio test. We already given that the limit exists and less than 1. Therefore, we can pick an arbitrary epsilon. We introduce r such that it's bigger than rho and less than 1, and let epsilon be the difference. Then by the definition of the limit of a sequence, the limit satisfies the following inequality for all n bigger or equal to n capital. After rearranging, we get that the next term is less than the previous term multiplied by r. And by the transitive property of inequalities, we can relate the next term to the previous terms. If we add up the terms, we now end up with a geometric series that converges since r is less than 1. Therefore, we apply the comparison test and conclude that the series converges given that the geometric series does. However, this result applies when n is bigger or equal to capital N. Since we can add finite terms to a convergent series without affecting the convergence, we conclude that the series converges. These applications are not the only ones that uses the geometric series. The geometric series goes above and beyond. Hope you enjoyed the video, and see you in the next one.